Hi, in this video I would like to explain how does an induction cooktop work. An induction cooktop looks very much the same as any other ceramic cooktop. The cooking surface is usually made of tough, heat-resistant glass ceramic, and there are distinct zones where you can place your pots and pans. However, inside each cooking zone there's tightly wound coil of metal. We can explain its role experimentally. To carry out the experiment we need a big metal coil, a DC power supply, and a few small magnetic needles that can rotate almost without friction. When we place the magnetic needles around the coil, they will all indicate the direction of the Earth's magnetic field. However, when we connect the coil to the power supply and turn it on, the needles will still all align themselves to point towards different directions. As magnetic needles always indicate the direction of the magnetic field in which they are placed, this means that the electric current flowing through the coil generates a magnetic field around it. A direct current produces a constant magnetic field, which is easy to show but would be useless in an induction desktop. Therefore, an induction desktop uses alternating current, which generates an alternating magnetic field. However, a magnetic field, either constant or alternating, can't produce heat directly. To explain how a constantly changing magnetic field can produce heat indirectly, we need to carry out another experiment. In the experiment, we will use a big metal coil, a bar magnet, and a microammeter or galvanometer. When we connect the coil to the galvanometer, it shows no electric current in the coil. When we move the magnet towards the coil or away from it, the galvanometer shows a current flowing through it, which means that a variable magnetic field can generate an electric current in a metal wire. We can also show that a variable magnetic field can induce eddy currents in a piece of metal, not necessarily flowing through a wire. To do this, we need a long metal tube, for instance a copper or aluminum one, and two neodymium magnets that can easily move in it. We might also use a plastic tube, which does not conduct electricity, to show that the effect we observe really comes from eddy currents flowing in a metal tube. In the experiment, we hold a metal and the plastic tubes vertically and allow magnets to fall inside them. We observe that the magnet in the metal tube falls much longer than the one in the plastic one. We can also check that a magnet falls much longer in a copper tube than in an aluminum one. It is so because the resistivity of copper is lower than that of aluminum, so the intensity of the current induced in the copper tube is bigger. As we know from our first experiment, an electric current is a source of a magnetic field, and the magnetic field exerts a force slowing down the movement of the magnet. By the way, both aluminum and copper are non-ferromagnetic metals, so we can't attribute the effect to their magnetic properties. Now, we can sum up the results of our experiments and use them to explain the operation of an induction cooktop. When an alternating electric currents flow through the coil of copper wire placed under a cooking zone, it generates an alternating magnetic field just over the cooking surface. The field penetrates into the metal of the bottom of a pot standing there and induces eddy currents flowing around in it, which change their direction in accordance with the current flowing through the copper coil. These eddy currents flowing through the resistance of the pot produce heat in it. For nearly all models of induction cooktops, a cooking vessel must be made of or contain a ferrous metal such as cast iron or some stainless steels. In such metals, due to a larger skin effect, the depth of penetration of alternating electrical currents inside the conductor is smaller, which results in a higher resistance and hence a greater amount of heat generated. If the metal is too thin or does not provide enough resistance to current flow, heating will not be effective. Mass induction tops will not heat copper or aluminum vessel efficiently because the skin effect in them is much smaller and the currents penetrate deeper inside the metal, which leads to a much lower resistance and thus much lower heat production. All metal induction tops use much higher frequencies to increase the skin effect. Any vessel can be used if placed on a suitable metal disc which functions as a conventional hot plate. Induction cooking is quite efficient, which means it puts less waste heat into the kitchen, can be quickly turned off, and has safety advantages compared to gas stoves. Cooktops are also usually easy to clean because the cooktop itself does not get very hot.